Hello students, welcome to Educate. We are going to do numericals on the chapter 10 of class 11 physics. We have done till question number 8 in previous lecture. Now we are going to start from question number 9. So let's proceed. Question says a brass wire 1.8 meter long at 27 degrees centigrade is held taut with a little tension between two rigid supports. If the wire is cooled to a temperature of minus 39 degrees centigrade, what is the tension developed in the wire? If its diameter is 2 mm, coefficient of linear expansion of brass equal to 2.0 into 10 power minus 5 Kelvin, Young modulus of brass is given as 0.91 into 10 to the power 11. So you have understood the question. Now we are going to apply the concept of linear expansion and we can evaluate, right? So let's start. So here we write delta L equal to, you remember the formula, L equal to L0 1 plus alpha delta T. So from there this L0 is multiplied, so L minus L0 will become delta L, L0 alpha delta T, right? Now we are going to put values. So here we can do one thing, because we need, in this question there is one more point, Young modulus is given. It means we will need stress and the strain. So here strain can be evaluated, change in length divided by original length. So we write delta L upon L0 equal to alpha delta T. And here values are given, that of alpha and delta T. So we can write, so 2 into 10 to the power minus 5, and temperature change is here minus 39, so you can take it 39 and plus 27, right? Because minus 39 till it goes from 27 to this, so obviously it will be this, right? Then there is a relation, you know, Young modulus Y equal to stress upon strain. We have got strain from here, right? And we can evaluate stress. So stress will be equal to how much? Stress will be equal to Y times strain. So strain is this much, and Y is given in our question 0.91 into 10 to the power 11 into this value 2 into 10 power minus 5 into this will become 666, right? So we have got the value of stress that you can evaluate. So it will come out to be 1.2 into 10 to the power around 8 Newton per meter square. So you have got stress strain. Now next point is we have to find out what is tension. So tension is equal to, if you remember, tension is force per unit area is stress. In our question we have got a stress and we need this tension, so tension will be equal to stress into area. So just write here stress multiplied by area, right? So is area given in our question? So here diameter of the wire is given as 2 millimeter. So we can find the area after section, that will be pi r square. So we can put the values. So 1.2 into 10 to the power 8, right? Multiplied by area, pi into radius. The radius will be here, it is diameter is 2. So 1 into 10 to the power minus 3 whole square, right? Now evaluate it. So what will you get? You will get 3.77 into 10 to the power 2 Newton, right? So question is a little complicated, because here concept involved is, number one, this L equal to L0 1 plus alpha delta T, and you have to evaluate strain from here. Then this relation Young modulus y equal to stress upon strain, then we evaluate stress, and after that we reached till here. Then we have to find out tension, and tension is force, and you know stress equal to force upon area, tension upon area. So stress into area will give tension. So we have got the answer, right? Now we are going to see next question. Next question says a brass rod of length 50 centimeter, diameter 3 mm is joined to a steel rod of the same length and diameter. What is the change in length of the combined rod at 250 degrees centigrade if the original lengths are put at 40 degrees centigrade, right? So here temperature difference will be 250 degree minus 40 degree. Is there thermal stress? Do you remember the concept of thermal stress? When the wire is fixed at the two ends and heat is applied, then it will try to expand, but since there are limitations, so there will be thermal stress. Here what is happening? Is wire fixed? A brass rod of 50 centimeter and diameter this much is joined to steel rod of the same length and diameter. What is the change of length? Here nothing is mentioned, means it is free. If it is free, then thermal stress will not be there, correct? And here coefficient of thermal expansions of the two materials are given, so we can easily evaluate. So let's try. So for brass, we can evaluate delta L, same formula, L0 1 plus alpha delta T, right? So delta L will be how much? L0 is given, its original length. So what is that? Its alpha is given this much and original length is 15. So 0.5 into 1 plus alpha is 2 into 10 to the power minus 5 into temperature difference is how much? It is 210, right? So delta L for brass can be calculated, and that this will come out to be 0.21 centimeter, right? Then for steel we can evaluate delta L. So it will be again same formula, L0 into 1 plus alpha delta T. We put the values. L0 length of this brass rod is given, and a brass rod of this and diameter this much, steel rod of same length and same diameter. So for steel rod it again same thing, and 1 plus alpha for steel is given 1.2 into 10 to the power minus 5. Temperature change is same as 210. Now we evaluate it. So what do we get? It will come out to be around 0.13 centimeter, right? This was 0.21 centimeter, this is 0.13 centimeter. And now we have to find out change in combined length. So change in combined length will be, so suppose we write delta L1, this is delta L2. So delta L will be delta L1 plus delta L2. Now we can put the values. So this will become 0.21 plus 0.13. That will come out to be 0.34 centimeter, right? So you have got the answer, and as I have told you that there is no thermal stress because the two ends are not fixed. Now we are going to see next question. What does next question says? Next question says the coefficient of volume expansion of glycerine is this much. What is the fractional change in density for a 30-degree rise in temperature? So gamma is given, and we have to find out fractional change in density. It means new density minus old density divided by old density we can evaluate. So let's see how. So first of all, we are going to see the relation how gamma is related. So if you remember the formula, V equal to V0 1 plus gamma delta T, right? So we can find gamma. So gamma will be equal to, from here V minus V0 we can do. So gamma, sorry, here gamma means, you remember as I told you, so gamma, this alpha V is equal to gamma, because three types of expansion coefficients we have discussed. One is linear expansion, denoted as alpha L, another is alpha A, and third one was alpha V. So here we are talking about alpha V. Either you can write alpha V if there is slight confusion. So in place of this, now let's put the values. So we can evaluate gamma or alpha V. That will come out to be Vt, means this V minus V0 divided by V0 times delta T, right? And then if you remember, mass upon volume equal to density. Here we are given volume, so volume will be mass upon density. So we can write m upon rho minus m upon rho 0 divided by m upon rho 0 times delta T. Up to here there is no doubt. Now m can be removed and we can rearrange it. So it will become rho 0 minus rho divided by rho 0 into delta T, correct? So you have got alpha V. Now what is to be done? You need fractional change in density. So fractional change means rho 0 minus rho divided by rho 0. So take the delta T to this side. So rho 0 minus rho divided by rho 0 equal to alpha V times delta T. Put the values. Are values given? So here coefficient of volume expansion is given 49 into 10 power minus 5. So we can write it 49 into 10 to the power minus 5 into delta T, change in temperature, is 30 degree. Just evaluate it. What do you get? It will be around 0.01, 0.0, then 1 and 4, 7. Correct? So I think you have understood. Let's see next question. Next question says, this question, a 10 kilowatt drilling machine is used to drill a bore in a small aluminum block of mass 8 kg. How much is the rise in temperature of the block in 2.5 minutes, assuming 50% of power is used up in the heating the machine itself or lost to the surrounding? Specific heat of aluminum is this much. Here you have read the information. Here power used is given. Power means energy or work upon time, and you know that efficiency is just 50%, means total energy. If total energy is E, then E by 2 is used for heating purpose. So these are things we are going to take into consideration, and after that we are going to solve the problem. So let's see how can we proceed. So first of all, we have to find out the energy, and energy equal to power into time, right? And we have power in our question as 10 kilowatt. So 10 into 10 to the power 3 multiplied by time taken is 2.5 minutes, that is 2.5 into 60, right? So just evaluate it, it will become 1.5 into 10 power 6 joule. So we have got the energy requirement, and only 50% of it is used up. So let's see 50%. So heat absorbed is 50%, 50 by 100 of this 1.6 into 10 to the power 6. Sorry, 1.5 into 10 to the power 6. So this will come out to be 0.75 into 10 to the power 6. Up to here there is no problem. Now we can apply formula Q equal to ms delta T, right? So in place of Q we have this much, and mass is given in our question, and specific heat is also given. So let's put the values. So our concern is to get delta T. So delta T we can evaluate from here. Delta T will be equal to Q upon MS. Q is 0.75 into 10 to the power 6 divided by mass. So mass is 8 kg and the specific heat is 0.91. Just evaluate it. So after evaluation, you will get around 103 degrees centigrade. Some fractional parts will also be there that you can do. I think if you do the calculation, you will understand. Now, let's go to next question. We have done question number 12. Now, let's go to question number 13. The question 13 says, a copper block of mass 2.5 kg is heated in a furnace to a temperature of 500 degrees centigrade. Then placed on a large ice block. What is the maximum amount of ice that can melt? Specific heat of copper is this much, heat of fusion of water this much. You understood? Here first of all we have to find out what heat is given by this block, which is at this much 2.5 kg block at 500 degrees centigrade, and since it is melting the ice, so ice will have certain latent heat and then it will melt and then its temperature will rise. So these are things we are going to see. And how we will evaluate then latent heat concept. You remember Q equal to ml, and if we apply another formula Q equal to ms delta T, then we can take the temperature change into use. So let's see, let's analyze the question. So question says heat lost by copper. So heat lost by copper is equal to mc delta T. C is specific heat of copper. Mass is given 2.5 into 10 to the power 3 and specific heat of copper is 0.39 multiplied by temperature change is 500 degrees centigrade, because from 500 it is melting the ice, so ice is at 0 degrees centigrade. So that's it. So we can evaluate it. Then heat gained by ice. Here heat will be used for melting, so we will apply ml, right? So m is to be determined and L is given in our question. How much? 335. Right. Now we can apply the concept of calorimetry. Heat gained equal to heat lost. Alright. So we can say m into 335 is equal to 2.5 into 10 power 3 into 0.39 into 500. Now what all is left? You have to find out what is m. So think 1 minute, just divide it. So it will come out to be around 1.455 kg, right? I think you have understood the concept of calorimetry is put into use to solve this problem. Now, next question. In an experiment on the specific heat of metal, a 0.2 kg block of the metal at 150 degrees centigrade is dropped in a copper calorimeter of water equivalent 0.0025 kg containing 150 centimeter cube of water at 27 degrees centigrade. The final temperature 40 degrees centigrade. Compute the specific heat of the metal if heat losses to the surrounding are not negligible. Is your answer greater or smaller than the actual value for specific heat of the metal? Here, if heat losses, to the surrounding are not negligible. So let's see, but let's think about the question. Here, it's given specific heat of metal at this degree containing this in an experiment on the specific heat of metal. 0.2 kg block of the metal at 150 degrees dropped in a copper calorimeter. Here, mass of copper calorimeter is given in terms of water equivalent, so that will make our calculation easier. This is volume of water given 27 degrees centigrade, final temperature is this much, means there is gap of 13 degrees centigrade, specific heat of metal is to be found, and heat losses to the surrounding are not negligible. In that case, what will happen? So let's analyze the question. So heat lost by metal block, let's see. So heat lost by metal block. We can apply formula MC or MS delta T. So MS delta T. Specific heat can be written as either MC delta T or MS delta T. Both are same. So don't get confused. And it is 200 mass, and its specific heat is say C, and temperature change is 110. Say this value is in calorie. Right. Now we have to check total amount of water. So water plus water equivalent. So amount of water will be actual water, that is 150 gram, plus water equivalent, that is 25 gram. So it is 175 gram. Right. Now, so, and the specific heat of water, specific heat of water, it is 1 calorie per gram per degree centigrade, right? So we are using CGS. So now what more? So here amount of water is, so we have got heat lost by metal block is this much, and heat gained by water and calorimeter can be calculated. So let's evaluate. So heat gained will be, again same formula we will apply. So heat gained will be equal to heat gained. We can write this total mass, that is 175 into specific heat. We are taking 1 calorie, temperature difference. So here, what is temperature? So 40 degree to 27 degree. So 40 minus 27, that is 13 degree, correct? Now, if we apply again principle of calorimetry, so heat lost equal to heat gained. So by principle of calorimetry, heat lost equal to heat gained, right? So put the values, that is 200 multiplied by C multiplied by 110 is equal to 175 into 13. So what do you get? C equal to how much? This divided by this, just do it. So it will become 0.1 calorie per gram per degree centigrade. 0.1 calorie per gram per degree centigrade, right? So this question is also simple and based on the concept of calorimetry, in which heat gained and heat loss are equal. So you have understood the question. Now next question, let's see. Next question says, so in next question some information is given. Molar specific heat of hydrogen, nitrogen, etc. The measured molar specific heats of these gases are markedly different from those for monatomic gases. Typically, molar specific heat of a monatomic gas is 2.92 calorie per mole per Kelvin. But here, explain this difference. What can you infer from the somewhat larger value of chlorine? And chlorine differs. So actually, see, when we talk about degree of freedom, so if there is vibrational degree of freedom, in that case what happens? In that case, molar specific heat will increase. So in case of chlorine, there must be vibrational degree of freedom also. So that could be the reason. And in other cases, we are just considering normal. If we are considering diatomic, then degree of freedom will be 3. So not 3 but 5. In case of monatomic, it will be 3 because formula says 3n minus k. Degree of freedom is given by 3n minus k, where k is number of independent relations and n is number of particles. So here for single, if n equal to 1, then there won't be any other relation. So k will be 0. From there we will get degree of freedom as 3. But if n is 2, in that case what happens? This will be 6 and there will be one relation, so 5. But if vibrational mode is also involved, in that case 2 more degree of freedom will come into play and thereby f will increase. Correct? So later on we will study these things, but here our concern is just see what is happening. So in this question, what is to be evaluated? So different CVs are there. If we use the gas constant typical value, we can get certain relations like here if we evaluate CV. So CV is given by 5 by 2 R. There will be a question in your mind, but I will tell you in a minute. Before that, let's do this question. R is a gas constant whose value is 8.31, and if we convert in terms of calorie, then we have to divide by 4.2, which gives 5 calorie per mole per Kelvin, right? So this will be around 5 calorie per mole per Kelvin, right? So that is the value. Here, as I told you, in case of chlorine, there must be vibrational mode also. And if you want to know why this, so there is very simple concept. So we find energy. So let's consider one single molecule. Right. So in case of single molecule, what happens? Degree of freedom will be 3, right? And each degree of freedom has energy half kBt, where kb is Boltzmann constant. So for 3 degree of freedom, energy will be how much? It will be 3 by 2 kBt. And if you are considering diatomic molecule, then in place of this, degree of freedom will be 5, as I told you, because the degree of freedom is given by 3n minus k, and n equal to 2, k means one relation, so f will be 5. In that case, energy will be 5 by 2 kBt. And if we consider 1 mole, so in that case you have to multiply, total energy will be, say it is U in that case, so Na, Avogadro number, multiplied by this value 5 by 2 kBt, right? And if you remember, Na and Kb, the product of these two gives gas constant U equal to 5 by 2 RT, right? And CV is equal to du upon dt. So if you differentiate it with respect to t, you will get 5 by 2R. So that was the requirement of our question and we got the answer, correct? Now, let's see next question. A child running a temperature 101 degree Fahrenheit is given an antipyrine, a medicine that lowers fever, which causes an increase in the rate of evaporation of sweat from his body. If the fever is brought down to 98 degrees Fahrenheit in 20 minutes, what is the average rate of extra evaporation caused by the drug? Assume the evaporation mechanism to be the only way by which heat is lost. The mass of the child is 30 kg. The specific heat of human body is approximately the same as that of water. And latent heat of evaporation of water at that temperature is about 580 calorie per gram. So let's see the question. So question says that this child is having temperature 101 degree Fahrenheit and his temperature drops to 98 degree Fahrenheit. Right. So let's put the values in the standard form. So here delta T is given 3 degree centigrade. That is clear. 3 degree Fahrenheit. If we convert in degree centigrade, then 3 times 5 by 9. So this will become 5 by 3 degree centigrade. Up to here there is no problem. And the specific heat of human body, here specific heat of water we will take for human body. So specific heat of human body is equal to specific heat of water. Right? Specific heat of water, and that will be 1 calorie. So 1 calorie per gram per degree centigrade. Gram per degree centigrade. Correct? So heat lost. So let's find out what is heat lost. Same formula, ms delta T. So what is mass? So mass of the child is 30 into 10 to the power 3, and the specific heat of body is 5 by 3, not 5 by 3. This is temperature change 5 by 3, and specific heat is 1. So 1. So it will become around 50,000 calorie. Correct? So this is heat lost. Now here heat gained by the sweat, because sweat will evaporate without changing temperature. So we will apply concept of latent heat. So we say that suppose m gram of sweat is evaporated. So mass of sweat we take as m gram, and latent heat is given in our question. It is how much? 580. Yeah, so let's apply that. So we say m dash into 580 must be equal to heat gained total, and that is 50,000 we found earlier. So m dash, mass of sweat, we can evaluate. So 50,000 divided by 580, right? So if we simplify, so it will become 86.29 gram. 86.29 gram. Now rate of evaporation is equal to total mass of sweat, m dash, divided by time. So m dash is 86.29 divided by time taken how much? And it is how much? In 20 minutes. Right, so 20 minutes per minute, in terms of per minute we can write. So this will become 4.31 gram per minute. Correct? So I think you have understood. Now let's take next question. Next question says, a thermopile icebox is cheap and an efficient method for storing small quantities of cooked food in summer. In particular, a cubical icebox of size 30 cm has a thickness of 5 cm. If 4 kg of ice is put in the box, estimate the amount of ice remaining after 6 hours. The outside temperature is 45 degrees centigrade and coefficient of thermal conductivity of the thermocol is 0.01 joule per second per meter per Kelvin. Heat of fusion is 335 into 10 power 3 joule per kg. So question is not tough, so we can do it easily. So let's see how to do. So we find surface area first. So what is surface area? So surface area, there are 6 spaces. So 6 times a square, and we can evaluate, we can put the value 6 times 30 into 30, 30 into 30, this will be in cm square, which can be written in terms of meter square, 0.54 meter square. Up to here there is no problem. Now here x is given as 5 centimeter, this thickness, x equal to 5 centimeter. And what about time? So time is given 6 hours, t equal to 6 hours, that is 6 into, in terms of second if we write, so 3600 second, right? So temperature difference T1 minus T2, T1 minus T2 is given 45 degree centigrade, right? And what more we need? Value of k is also given. So what is k? K is given as 0.01 unit. I'm not writing because June 2nd, that is clear. Now what is to be done? So if you remember, Q, rate of heat transfer, we have studied. So Q depends on area, temperature difference, time, and inversely proportional to distance between the faces. If you remember this concept, we are talking about this concept that if heat is supplied to one face here, then it will get transferred. This temperature T1, this is T2, this is X, and time is, say, T. In that case, formula. So Q equal to Ka times T1 minus T2 times time divided by distance. This is basic formula, right? So here we can evaluate it. So what will it be? So here we assume that mass of ice that melts is m, and then we can apply formula Q equal to ml also, right? And then we can equate. So first of all, we have to evaluate what is Q. That is the main question. So Q equal to K, value of K we can write 0.01 into area, 0.54 into temperature difference, it is 45. And then time is given as 6 into 3600, it is clear. And separation is just 5 centimeters, 0.05 meter. Now we evaluate it, this comes out to be 4976 joule, right? So this is the heat. Now as I told you, here latent heat Q equal to, we have to apply ml, and our concern is to get m. So m equal to Q upon L, and Q we have got this. Latent heat we can divide 104976 divided by latent heat is given as heat of fusion 335 into 10 to the power 3. Now simplify, this will come out to be 0.313 kg, right? So this much ice melts, then remaining ice, what was amount in the beginning, you can subtract 6 kg it was in the beginning, and this much is melt, then remaining amount you can easily calculate. Sorry, I think I told you nothing here. 4 kg, this is another question. So ice was 4 kg and this much melts, then remaining ice you can find 4 minus this much, correct? Now let's see question number 18. A brass boiler has base area this much, 0.15 meter square, and thickness 1 cm. It boils water at the rate of 6 kg per minute when placed on a gas stove. Estimate the temperature of the part of the flame in contact with the boiler. Thermal conductivity of the brass is given. Heat of vaporization of water is given. Again same question. So same concept we are going to use. So here information is given. First we will write Q equal to same formula, Ka T1 minus T2, T1 minus T2 times time divided by X. We put the values. K is given 109 into A. What is A? A is 0.01 15 into temperature change. T1 is not known, T2 is 100, and time is 60 divided by separation is given as 0.01. We can leave it here, and then mass of water that boils. So mass of water, so this is 6 kg, right? And now in terms of gram, if you want to write, so this will become 6,000 gram, no problem. Then heat used to boil the water. Heat used to boil the water. So it will be amount multiplied by heat required, that is 2256 into 10 power 3. So here if we use in gram, then this will be 2256 only. 2256, right? Now what you do, these two heats, they must be equal. You can equate. So if you equate, what do you get? So you can write this value here. You can start from here. You take this value here, 6000 multiplied by 2256, right? Our concern is to get T1. Just evaluate it. You will get around 238 degrees centigrade. Calculation is your part, that is why I'm not doing. I think you can easily do. And question number 19 is theory question that you can read and do. Let's do last question of the exercise. Here, a body cools from 80 degree to 50 degree in 5 minutes. Calculate the time it takes to cool from 60 to 30 degree. The temperature of surrounding is 20 degree. So if you remember Newton's law of cooling, so we are going to apply that, and the question can be easily solved. So as we have discussed, it is MC T1 minus T2 divided by time is equal to K times average temperature T1 plus T2 divided by 2 minus surrounding temperature. This is basic concept, right? So we can put the values. So MC times T1 minus T2, so 80 minus 50 divided by what is time? Time is 300 seconds, correct? Because it is 5 minutes, equal to K times T1 plus T2. Average, so 130 divided by 2, 65 minus 20, right? We can treat it as equation number 1. Then again here 60 to 30. Same concept, we can take MC and 60 minus 30, and time is unknown, equal to K times average temperature. So 60 plus 30 divided by 2 minus room temperature 20 or surrounding temperature 20, correct? If you divide the two equations, what do you get? The second equation. So if you divide the two equations, you will get, it is simple. So 30 upon 300 into T upon 30 will be 45 by 25. That is simple. You can evaluate. Just simplify it. So from here, you will get value of T as 540 seconds, or this is equivalent to 9 minutes. So this is how you can solve this question. I think you have understood, although I solved some questions with the speed, but I think you are enough intelligent to understand the steps. And this is how lesson is over. Thank you for watching. Team Educate